All right, silly people, here's the situation. We just have, it's a three-dimensional harmonic oscillator, um, which I've drawn in the form of springs, um, kind of poorly. Uh, the thing to recognize is that the harmonic oscillators are pretty much going to be causing a potential that it's a Hooke's law potential in three different directions at once, but K1 is equal to K2. So that means that we're going to have some degeneracy somewhere where a couple of the um, frequencies at the end of the problem are going to be dependent on the other. Um, and then it wants us to solve this in cylindrical coordinates to represent this. So I'm just going to get right into it. Kinetic energy in um, cylindrical coordinates is given by m over 2 r dot squared plus r squared theta dot squared plus z dot squared. And the potential is just, again, it's just three different Hooke's law potentials on top of each other. So k1 over 2 x squared plus k1 y squared over 2. The x and y springs are the same. There's supposed to be a y there. Yeah. And then there's a k3 z squared over 2. To convert this potential into sphere or cylindrical coordinates, that's not too hard because r squared is just x squared plus y squared. That's an easy substitution. So we can rewrite the potential as k1 over 2 r squared plus k3 z squared. That's supposed to be a z squared up there over 2. All right, which means the Lagrangian t minus v looks like this. C dot squared minus k1 over 2 r squared minus k3 over 2 z squared. All right, we can get towards constructing our Hamiltonian by first finding the canonical momenta, as always. dl dr dot. Sorry, my cat is trying to destroy my computer. dl dr dot is just mr dot. Del L del theta dot will be mr squared theta dot. Look at that negative momentum. Del L del z dot will be just mz dot. And that's going to be our PR, P theta, and PZ. As always, just go ahead and put R dot and theta dot and Z dot in terms of the momenta. So we'll have that. So we'll have P theta over MR squared equals theta dot. And PZ over M is equal to Z dot. Rewrite the Lagrangian in terms of that stuff. We'll have M over 2 PR squared over M squared plus P theta squared over M squared R squared. Yeah, and then PZ squared over M squared minus the potential terms. And then I'll just simplify this stuff here. That's all going to be p squared over 2m theta squared over 2m r squared pz squared over m or 2m minus k1 over 2 r squared minus k3 over 2 z squared. That's the Lagrangian. The Hamiltonian then, as always, is this time is going to be p r dot plus p theta theta dot plus p z z dot minus the Lagrangian. We can use our definitions of the r dots and theta dots and z dots to write all of that stuff out. It's going to be p r squared over 2m p theta squared over 2m r squared and pz squared over 2m minus the Lagrangian, so this stuff. Actually, that's not 2. I'm jumping the gun. Minus p theta squared 2m r squared pz squared 2m plus k1 over 2 r squared plus k3 over 2z squared. Makes it look a lot like your classic Hamiltonian for the simple harmonic oscillator, but with 3 dimensions. And one of them is weird because it's divided by r squared, which is kind of why it's interesting to try and look at this in such a way as to eliminate degenerate frequencies. Right, that's the Hamiltonian. This this thing has terms of r and z, but noticeably doesn't have any terms of theta, which means it's cyclic in theta, which means this time we're going to be writing our Hamilton's principal function as we're going to have a characteristic function of r, a characteristic function of z, and then a constant alpha theta, which is going to be angular momentum, times theta, and then minus alpha r times t minus alpha z times t. So that when we write our Hamilton-Jacobi equation, we're going to have, we're going to go ahead and have p theta just become alpha theta, because that's just del s del theta anyway. We won't write the rest of the momentums in terms of the derivatives of the functions. We'll just use that one, alpha theta, and rewrite this stuff. I'm going to bring out a 1 over 2m pr squared plus p theta squared. That is now alpha theta squared over r squared plus pz squared plus k1 over 2 r squared plus k3 over 2z squared. In the Hamilton-Jacobi equation, this will be equal to alpha r plus alpha z. Awesome. So this is a partly separable Hamilton-Jacobi equation. You want to separate the stuff that depends on r from the stuff that depends on z, and then solve for the integrals. I'm going to do the z stuff first, because the r stuff is gross. The z stuff is just pz squared over 2m plus k3 over 2z squared is equal to freaking alpha z. We can solve for p z, which will give us 2m alpha z minus k3 m z squared under a radicand. And then the action jz will just be the closed loop integral of pz with respect to z. This is very similar to a previous problem that I've done. And so I'm not going to write the bounds of this integral just yet, because as it turns out, it's not going to matter at all because it's substitution time. I'm just going to call z equal to the square root of 2m alpha z over k3m sine theta, so that the z differential will just be that radical times cosine theta. D theta. And then rewrite the integral, so jz will be root 2m alpha z over k3m. And then inside the integral we'll have cosine theta square root of 2m alpha z minus 2m alpha z sine squared theta d theta. Then we can go ahead and factor out the 2m alpha z. I'm going to leave the m's inside of the radicand so that we'll have 2 alpha z times the square root of m over k3. And then the integral is just going to end up being cosine theta times 1 minus sine squared theta d theta, which is just going to be the closed loop integral of cosine squared theta d theta. That's a really gross d. So that's a trivial integral. That's 2 pi alpha z root m over k3. We can go ahead and solve for alpha z in terms of the action, which is going to be jz over 2 pi times the square root of k3 over m. All right, nothing too difficult there as compared to our previous problems. This is when it starts getting weird. We're now going to separate the r stuff out from our Hamilton-Jacobi equation. That's going to be pr squared over 2m plus alpha theta squared over 2m r squared plus what was the other term? It was just k1 over 2r squared. Yeah. k1 over 2 r squared is equal to alpha r. And we're going to solve for this momentum. And it's going to turn out that the new integral is going to be really gross. 2m alpha r minus alpha theta squared over, it's just going to be over r squared plus k1 m r squared under a radicand so the action JR will be that stuff under, right, we're going to be integrating over a closed loop of PR dr, which is this junk here. Copy, paste. Now, this integral is going to give us a complex result because it's a contour integral. in the chapter that Goldstein talks about this, he actually uses a contour integral um, to solve the Kepler problem, I think, with a transformation, something like that. Um, and I bring it up because we're going to make this integral look the same as that integral that he was using before in that chapter, using a couple of clever substitutions so that we don't have to do contour calculus. U is equal to r squared, with du being 2r dr, and then rewrite the integral here. Um, it'll be 2r times the square root of 2m alpha r minus alpha theta squared over u plus k1m u. I haven't done anything too egregious yet. I'm also going to go ahead and put u in terms of r. So that'll be actually 2 times the root u times all that stuff. That's supposed to be over u. du, and that's supposed to be du there. Whoops. And also, I did this wrong because it's going to be actually 1 over 2r and 1 over 2 root u there. I'm going to factor through that root u into the radicand and take the 1/2 back out so that we'll just have 2m alpha r over u minus alpha theta squared. Oh, it's over u squared. Alpha theta squared over u squared plus k1m. Cool, cool, cool. Now I got to make another substitution. Okay. So this time the substitution is v is equal to 1 over u, where the differential dv will be minus 1 over u squared du. Yeah. So we'll go ahead and put that stuff in to the integral. So that'll be minus 1/2 integral u squared square root. I'm going to go ahead and put u in terms of v actually. U squared will be 1 over v squared. So we have 1 over v squared there. This is going to be 2m alpha r v minus alpha theta v squared plus k1m under the radicand dv. This is the integral. This is of the same form as Goldstein quotes in the book, where he has a closed loop integral of minus 1 over z squared times the under the radicand a plus 2bz minus cz squared dz is going to be equal to 2 pi I square root negative c plus b over root a. Every time. Doesn't matter what the bounds are. So I'm going to go ahead and then change over what I have in my radicand to what he has. So A is going to be k1m 2b is equal to 2m alpha r, and c is just going to be alpha theta. Yeah. Okay. Putting all that stuff in, we'll have a minus, the integral, I mean, will be all multiplied by 1/2 of 2 pi I minus, or whoa, the square root of minus alpha theta plus b divided by the square root. I think I made an algebra mistake way back. Yeah. These are all meant to be minus signs, actually. Minus, minus, minus. I need to do this because it's going to make things not be imaginary in the end. We want real action angle variables. So that means A is actually minus km, minus k1m, minus k1m here. B was just m alpha r. So we have a couple of radicands which have an I factor, or there's negative signs into the radicands. I'm just going to go ahead and deal with those. That's going to be I times root alpha theta plus m alpha r over I root k1m. And then make it so that for the second bit, the I is actually on top. So it'll be now minus I m alpha r over root k1m. And then the i's will cancel out, so it'll just be now pi times m alpha r times root, or divided by root k m minus alpha theta. That is the action, JR. Now we can finally solve for alpha r. It'll be JR over pi plus root alpha theta, all multiplied by root k over m. Fantastic. Now we can put the Hamiltonian in terms of this stuff. So remember, the Hamiltonian ended up being equal to alpha r plus alpha theta, or no, alpha r plus alpha z. So we're just going to add these up. H equals JR over not 2 pi, just single pi, plus square root alpha theta times root k1 over m and I've already forgotten what jz was, or what alpha z was, so I'm just going to go up and copy it. There it is. Jz over 2 pi times root k3 over m. Snagged. Cool. Now we have to solve for j theta. We don't even have the action in terms of theta yet, which is j theta equals the integral of p theta d theta. But p theta is just a constant. It's alpha theta d theta. Um, so that means that this is just going to be 2 pi alpha theta. We can rewrite then alpha theta as being the square, or no, not the square root, just j theta over 2 pi. Then when we rewrite our Hamiltonian, uh, we'll have j theta on the inside, which is hella wacky. Also, I think I did this in a silly way. Where did I mess up? Oh, this is supposed to be squared, so this is going to be squared, so that's going to be squared, so it's actually not square root of alpha theta, but just alpha theta. Just alpha theta. Just alpha theta. That helps. So that we can just go ahead and rewrite the Hamiltonian in terms of all the actions now. 2 pi root k1 over m plus jz over 2 pi root k3 over m. Yeah. Fantastic. We can now get all of the different frequencies for this system. Let's just do nu r, which is del h del jr is going to be 1 over pi root k1 over m. And then nu theta is del h del j theta, 1 over, which is just 1 over 2 pi root k1 over m. This is what I mean by having degenerate frequencies. It's not too hard to see that nu theta is just 1/2 of nu r. So it doesn't even have like its own special dependence. It's just the same frequency divided by 2. And then nu z is just, we write out the derivation to del h del jz 1 over 2 pi root k3 over m. Okay. Normally that would be the end of the problem, but Goldstein does ask us to rewrite now the Hamilton-Jacobi equation in a coordinate system that isn't degenerate and will only collapse into 2 different frequencies rather than 3. That is just the same as one of the other ones. To do that, just following through what Goldstein does, you can rewrite the degeneracy as nu r minus 2 nu theta as equal to 0. The generating function for our transform coordinates will then be f equals j1, is a new quantity. J1, J2, and J3 are going to be our actions in our transformed coordinate system. On the inside of these parentheses, we'll have WR, not omega. W just being the letter that Goldstein uses for angles in the action angle formalism, where it's just it's W dot is equal to nu for each of these guys. So the degeneracy will show up for the J1 variable. J2 will have a W theta multiplied by it, and J3 will have a WZ multiplied by it. Then we're going to define our transform coordinates so that J1, J2, and J3 are just multiplied by W1, W2, and W3 respectively. And so the new transform coordinates will be, or W1 will be WR minus 2 W theta. W2 will be the same as W theta. W3 will be the same as WZ. The transformation equations for the actions then will be JR is equal to J1, J theta is equal to minus 2 J1 plus J2, and Jz is equal to J3. I'm leaving out the derivation of that because really simple formula to use. It is in the chapter, and it's just a summation of terms and constants that you use throughout the problem that end up giving you the right transformations of actions. So now we can rewrite the Hamilton or the Hamiltonian now using these J1s and J2s and J3s. We had JR over pi. Now it's going to be J1 over pi. We had J theta over 2 pi. Now it's going to be J2 minus 2 J1 over 2 pi. And then we had J3, oh no, it's all multiplied by root k over m. Haha. Plus J3 over 2 pi root k3 over m. Multiplying the first fraction inside of these parentheses by 2 so that we have the same denominators, you can see that the J1s will actually cancel each other out, and we'll just be left with J2. Which, in a more efficient manner, displays the fact that there's really only 2 actions in this problem, J2 and J3. And consequently, really only 2 different frequencies. Which will be dependent on the spring constants. Through the same process that we did before, we can calculate these new frequencies, which we'll call nu 2 and nu 3, which is just del h del j3, which is now just 1 over 2 pi root k over m, and we'll have nu 3 be del h del j3 1 over 2 pi root k3 over m. 2 frequencies, 3 springs. Interesting problem.